All right, welcome to the first video of suggested homework exercises for pre-calculus or for Calculus 1. We're going to be using the 11th edition of the Larson Calculus textbook for these exercises. So you can follow along with me here, or you can have the book open in WebAssign or in Cengage. I also have my TI-84 calculator. This is the online version. I have a big view of the screen for you so that it shows nicely in this window. And I'm going to show any work on the whiteboard here that I need to write out. So the first problem highlighted here, number 3, is our first example, and we're to tell whether we need pre-calculus or calculus to solve this equation or this question. And if we can use pre-calculus, we're supposed to solve it with the pre-calculus techniques we know. If we can't solve it with pre-calculus, we're to explain why and to try and use a graphical or numerical approach to estimate the solution. So we want to find the distance traveled in 15 seconds by an object traveling at a constant velocity of 20 feet per second. And the keywords here, I'm going to underline them here for you, are constant velocity. That tells us that we can use pre-calculus. So we're just going to use our distance, rate, time formula. Distance is equal to rate times time. Distance is going to be a rate of 20 feet per second times 15 seconds. And in dimensional analysis, our seconds will cancel. We have 20 times 15. It's going to give us a distance of 300 feet. Let's go ahead and look at our next problem, problem 7. We have secant lines here. So it'll help us to go ahead and plot this function here, y equals the square root of x. Second stat plot, second table setting here, we set our independent variable to ask. That'll be helpful to us when we set up our table here. And we're going to want to know the y values. We already have it for 4, but we're going to want 1, 3, and 5 to be calculated for us here. And we're going to sketch a graph for part A. So let's see if I have some. No. And 1, 2, 3, 4, 5, 2, 3. All right, so we have the points that I know are on the graph, 1, 1, and 4, 2, and 0, 0 are on the graph of the square root function, like so. And then I'm going to pick a different color here, like red, for the 0.11. Then I'm going to pick a color like green for the 0.3, 1.7, something that's right here, and different color like purple for when x is 5, and that point is up here is 2.2 something something. I've got that. And let me go back to good old blue here for when we have the point 4, 2. Okay, so this is 4, 2. This is this is 5, and then it's 2.361, 2.2361. Then we have, let's see, there, green is 3, 1.7, 3, 2, 1, and red we have 1, 1 exactly. So now I want to find the slopes using those approximations that we have. So call in this point here Q1. This point here is P. Call this point here Q2 and this point Q3. The slope of the line through P and Q1 is Y2 minus Y1 over X2 minus X1 is exactly 1/3, which is 0.3333. Slope of the line through P and Q2 is Y2 minus Y1 over X2 minus X1. So go back out to my home screen here, and this is 2 minus 1.7321, and it's going to be divided by 1, so this is approximately 0.2679, and then for the slope of PQ3, we're going to have Y2 minus Y1 over X2 minus X1 is 0.2361 over 1. So something between 0.2361 and 0.2679. These all were part B. Part C says that I think that the slope at point P is approximately 0.25 or 1/4. That's my best estimate based off of the number that is that we're approaching from the left and from the right there. Now let's look at number 9 here. To wrap things up, we have these two pictures here of our function y equals 5 divided by x. Let me stick that into my calculator here. 5 divided by x. And I'm interested now in the table here first, where I have x's 1, 2, 3, 4, and 5. So 1, 2, 3, 4, and 5. This is 2.5, 2.5, 1.6667, 1.25, and 1. So these are our heights here of our rectangles using the left-hand side for finding these. So widths will be 1. So our area here in this first case is approximately 1 times 5 is 5, plus 1 times 2.5 plus 1.6667 plus 1.25 for the last one. Let's add those together on our home screen to get an approximate area. 5 plus 2.5 plus 1.6667 plus 1.25 is going to give us an area of approximately 10.4167. And in the second case here, where we have 8 rectangles instead, we're going to have x as not just 1, but then 1.5, 2.0, 2.5, so on. So let me just set up my table here to have delta x's of 0.5 and start at 1, and it'll automatically calculate here for me. This will be 5, this will be 3.3333, and this will be 2.5, 2, 3.0 is 1.6667, 3.5 is 1.4286, 4.0 is 1.25, 4.5 is 1.1111, and then we have 5 will be 1, and we want left endpoints again of the first 8, 1, 2, 3, 4, 5, 6, 7, 8. I'm actually not interested in this last one right here. Okay, so this is going to be, widths will be 0.5 for everything, times my y values of 5 plus 3.3333 plus 2.5 plus 2 plus 1.6667 plus 1.4286 plus 1.25 plus 1.1111. So let's go ahead and do that on my home screen. 0.5 times 5 plus 3.3333 plus 2.5 plus 2 plus 1.6667 plus 1.4286 plus 1.25 plus 1.1111. And then we get an area here of approximately 9.14485. And we can compare those. We're getting a better approximation here. As we squeeze out more air, as we get more rectangles, to get an even better answer, we can use more rectangles is the idea. And we'll talk about that a whole lot more in chapter 4 when we get there, and we'll use more and more rectangles, and we'll get approximations by making the left side of the rectangle touch the graph, make the right side of the rectangle touch the graph. The right answer is somewhere in between, and we'll try and learn a process. We're going to talk about something here called a limit in chapter 1. We'll try and use a limit process to squeeze out all the air and hopefully get an exact answer. So that's one of the places where we're going. We're going to use this idea of this limit process to help us get an exact answer for the slope at a point. And we're going to try and use the limit process to help us get an exact area under a curve. Those are two big problems that we would like. We also have this idea in our first problem of an instantaneous rate of change that would be different from a average rate of change that we could do with pre-calculus, and we use the limit process to help us with that too. So those are all calculus problems that we can't do specifically with just the pre-calculus techniques. We can get close sometimes to the answer, but we can't get the exact answer without this new idea of a limit, which we will be talking about next. So see you for the next video.